Hello, my dear students. Welcome again in this nuclear physics class. In this today's lecture, we will discuss about the gamma decay. So, in which we will discuss about the interaction of gamma radiation with matter in brief, and then we will talk about the multipole transitions, that is the electric and magnetic transitions which occur with this gamma decay process, and we will discuss about the order of a transition and what are the various selection rules which tell us about these electric and magnetic transitions. And further we will discuss about the important numerical problems or the type of questions which can come in the competition exams related to these gamma decay and types of multipole transitions. So let us start our lecture. Gamma rays, they are electromagnetic transitions and which is having a very high frequency. So when atom decay, they emit alpha or beta particle to form a new atom, and maybe there are chances that the new atom which is formed, it is having some excited state, and these particles, the newly formed particle, come from this excited state to the ground state. So in this case, the excess energy when the particle which comes from the excited state to ground state, and it loses its energy in the form of these gamma radiations. And so this is a nuclear phenomena. So gamma rays, they are coming from the nucleus, and there are the examples which is given. So one is the visible light ray, another is the X-ray, and third is the gamma ray. So which is more penetrating? So the penetration power of any ray, it is dependent upon its energy. And energy using the Planck's law, it is the highest frequency, and they are low wavelength waves. So the more penetration power, the gamma ray, they are the having the highest penetration power. They can penetrate up to several centimeters depending upon its energy. And the wavelength of this radio wave, which is very high, of the order of the size of the building. As we are moving toward this, when the wavelength it is being decreasing and the frequency it is increasing, and you can see that the microwave, so their wavelength it is of the order of 10 to power minus 2 centimeter, and similarly the visible light, they are having the frequency which is of the order of 4000 to 7000 angstrom. And so the gamma radiations or the gamma rays, which is having very low wavelength of the order of 10 to power minus 12 centimeter, but very high frequency. And from that you can see that they can carry a very high energy of the order of tera electron volt. So they are the most dangerous type of radiations. So you have maybe studied about the gamma radiation interaction with matter. So when a high energy photon, a high energy gamma radiation, it is interacting on the surface of matter. So there are various type of phenomena which you can see, like the Rayleigh scattering, when there is no change of energy between the initial and final transition. So these are known as the coherent type of scattering, when the particle it loses some of its energy to by recoiling these electron, and they are known as the Compton scattering, which is the incoherent scattering example. And you have almost studied the photoelectric effect. So phenomena when a photon which is striking on any metal surface, and it can kick the electron from the metal surface
and this emission of electron, that is known as the photoelectrons, and this phenomena is known as the photoelectron. And the energy of this emitted electron, it is dependent upon the energy of these photons minus h nu naught. So this h nu naught, that is generally known as the work function or the threshold frequency of a material. If the energy of this photon, it is greater than the threshold frequency of any material, then it can easily kick the electron, otherwise there will be no photoelectric emission. And this equation, it has been given by Einstein, and on this equation he got the Nobel Prize for this discovery, that is emission of electrons from the metal surface. And this famous equation is known as the Einstein equation. So there is, students have confusion that the Einstein got its Nobel Prize for its mass energy relation, but the actual Einstein got its Nobel Prize for the discovery of this photoelectric phenomena. So another example of this gamma ray interaction, that is the pair production phenomena. So you all are familiar with this pair production phenomena. So if a very high energy photon or gamma radiation, which is of the order of 1.02 mega electron volt, and when they are striking to a metal surface and they come close to this nucleus, and when they come close to this nucleus, and there are chances that it is being absorbed by this nucleus, and on that cases it emits two particles. So one is positron and another is electron, and this phenomena is known as the pair production phenomena. And it only happens if the energy of this gamma radiation is of the order of 1.02 mega electron volt, so which is very, very high. So this has been seen in this space, that the pair production phenomena, and this equation is satisfying the Heisenberg uncertainty principle, because this positron, which is a very unstable particle, so this positron, it is formed for a time period of minus 10 raised to power minus 23 second, and again this positron, it interact with any electron which is free and within this space, and again this positron when elect with electron, and it forms a gamma radiation. So the occurrence of this pair production phenomena in this laboratory or in our laboratory analysis, it is very, very difficult. So we cannot generally see such type of phenomena in our daily life. So they are generally happening in this space, and they are very, very rare. So another example, you can see that the secondary type of interactions, when the gamma radiations, they are coming out from the nucleus, and there are chances they can interact with these orbital electrons, and when these gamma radiation, they lose some of its energy to the orbital electron, and they emit slow X-rays, which is known as the Bremsstrahlung phenomena. So Bremsstrahlung radiation, that is the wave breaking radiations. So you have all studied in this quantum mechanics or modern physics. I will not go in detail. And those electrons, so for example, if it is kicking the electron which is in the k orbital, and the high energy electrons, when they jump into this k orbital, and those electrons, they are known as the Auger electrons. So Bremsstrahlung radiation, that is due to the wave breaking slow X-ray radiation. So we will not study it in details. So these are some of the discoveries which I have mentioned in the photoelectric effect. So the energy of this emitted electron, it is dependent upon the gamma energy minus the binding energy, which is known as the work function. And so second is this pair production phenomena I have explained in brief. So why it is happening and when it is happening, when the energy of this gamma particle, it is of the order of 1.02 mega electron volt, or you can write it as 1022 kilo electron volt. So only in that case is this pair production phenomena, they are possible. So how these gamma radiation, they lose their energy. So how these attenuation, so this reaction is known as the attenuation. how the gamma radiation, they lose their energy when they propagate within the matter. And using the same reaction, you can see that the intensity of this gamma radiation, it is dependent upon this reaction. So I is the intensity after a particular thickness within the matter. I naught is the initial intensity of gamma radiation, and mu is known as the total absorption coefficient, and it depends upon what type of matter through which we are passing these gamma radiations. And on the basis of that, we can calculate these attenuation constant or the mass absorption coefficients of different materials. So they are having quite potential applications. Now we are talking, our main topic is related with gamma decay. So how gamma decay? So we know that gamma generally decay into electric or magnetic type of radiations. You have been studied in the electromagnetic because it is a EM radiation, so it is having both electric and magnetic fields. Now electric radiations from this gamma decay, it arises from change in distribution of electric charges in the nuclei, while the gamma magnetic radiation, they arises from the change in distribution of magnetic poles or in the current distribution within these nuclei. So how we can identify which type of electric radiation is being coming out or which type of magnetic radiation it is being coming out, and that we can calculate from the order of those reaction or order of pole. So that we can calculate with this equation that is of the order of 2 raised to power L. And L is known as the multipolarity of the order of the gamma transition. And if the value of L is 1, then it is generally known as electric dipole radiation or magnetic dipole radiation. So electric dipole radiation, it is generally represented with E1. Magnetic dipole radiation, it is generally represented with M1. And similarly, if the pole of the order of pole, it is of the order of 2. So 2 means the delta L, it is of the order of 2. So before, for the parent nucleus and after the gamma transition, and if the value of this delta L, it is of the order of 2, and that type of transition known as the quadrupole gamma transition. And here, if it is having E2 value, then we can generally call it as the electrical quadrupole radiation is coming out. And if it is having the magnetic transition, then we can call it as the magnetic quadrupole transition. Now L0 does not exist because no radiation is due to the transverse nature of the value of delta L, it does not equal to 0 always. So there is always a change of L value. So how we can find out whether the emitted radiation, it is a electrical dipole radiation, it is a magnetic dipole radiation, it is electric quadrupole radiation or magnetic quadrupole. So I have written here, so if the reaction, when there is an emission of gamma radiation, and if there is a change in parity, so if there is a change in parity, only those radiations, electrical radiation will come out which is having odd value. So electrical dipole transition which is having a change in parity which exists for -1, then it is for minus E3 transition, E5 transition, and similarly magnetic transitions which are having a even value, you can see M2, M4, M6, so and so. So we will do some numerical problems and then you will get the idea. So which type of transition is dominating for this particular gamma emission. So here I would like to mention that the transition probability, it decreases rapidly with increasing angular momentum change. So if there is a transition, there are possibilities that there is E1 radiation is coming out, there is cases E3 radiation is coming out, M2 radiation is coming out, M4 radiation is coming out. Then the maximum percentage or the maximum probability of the emission of E1, this is the dominant radiations. So these three, they are come out, but their probability is very less. So less probability, because the transition probability it decreases with increase in change of angular momentum. So these are some of the selection rules in order to find a electrical or a magnetic transition. So the possible values of delta I, so it can have a values which lies between II minus IF minus II and IF plus II. So IF, that is representing the angular momentum for the final nuclei, II representing the angular momentum for initial states. Initial state, IF, that is representing for the final state. And for electrical transition, we have to find the parity using this rule, minus 1 raised to power L. So if we can calculate first what is the value of L for a particular reaction, and if from the basis of L we can say so whether it is electrical radiation or a magnetic radiation. So if there is a change in parity, so this is very important, listen it carefully. So if there is a change in parity, so parity we generally identify with this equation. So parity of gamma radiation, that is the parity of initial state multiplied by parity of final state. So if there is a change in parity, then for E1, so these I will bifurcate here. So this is representing electrical radiation and this is representing the magnetic radiations. So if there is a change in parity, you can see here there is a change in parity with minus sign. So what type of electrical radiation will come out? E1, E3, E5, so and so, E7, and what type of magnetic radiations will come along with this electrical radiation? That is M2 and M4. And similarly, if there is a no change in parity, so if the parity is plus, so in that cases you can see E2 will come out, E4 will come out, and along with that M1 will come out, M3 will come out, M5 will come out, which is having no change in parity. So this is very important to understand, and depending upon the change in parity or how the parity it is being changed, we generally decide the order of electric and magnetic transitions. So this slide I have explained you that the electrical transitions, they are more probable than the magnetic transitions. So the probability of electrical gamma radiation, that is more as compared to magnetic gamma radiations. So let us do numerical related to this problem. So this is a question, find allowed multipole transitions for this particular reaction. So here initial state Ji, that is +1, and when the particle it jump from this +1 state to 2- state with this gamma ray emissions, we have to find what are the allowed gamma electrical and magnetic transitions for this. Now here you will see that the value of J, it depend upon using this equation. This equation is very important. The value of delta I or delta J, you can say it should be greater than equal to ji minus jf, ji plus jf. So here it is 2 minus 1 magnitude. So values of L will be equal to, or J will be equal to, you can say it is lying between 2 minus 1. So minimum value it has 1, and maximum value when we add this 2 plus 1. Ignore the parities. So don't look at parities yet. So maximum value of J which lie between 1 and 3. So J values which are possible for this transition are 1, 2 and 3 transitions. Now here no check at second step is to check their parities. So here it is plus parity, here it is minus parity. So parity is changing. So when parity is changing, so which type of electrical transitions are possible? E1, E3. So which are lying within this value 1 to 3, which are the values which lie, which is having a change in parity. So they only exist. And M2 it also lie between 1 and 3. So M2 transition is also possible. So allowed gamma transitions which are possible, they are E1, M2 and E3, and the majority or the maximum proportion of the transition which will come out, the maximum is of electrical dipole moment. So this is electrical dipole transition because it is E1, electric dipole gamma transition. These two values will also allowed, but their ratio is very less. Their probability is very less as compared to E1. So this is how you can calculate the allowed transitions for gamma selection rules. So this is another example. The ground state lead nucleus has a spin parity of 1 by 2 negative, while the first excited state has a parity of 5 by 2 minus. So always gamma transition is possible when it is coming from excited state to ground state. So it is coming from 5 by 2 minus to 1 by 2 minus. So what are the J values which are possible? So which are between 5 by 2 minus 1 by 2 to 5 by 2 plus 1 by 2. So maximum value, so when you subtract it, so it is 2 minimum, and maximum it is 3. So J values which are possible for this transitions, they are 2 and 3. Now our second step is to check parity. So there is no change in parity. So when there is no change in parity, so you can see that electrical transitions, which is there is no change in parity, so that is only E2 transition, and magnetic, that is the odd transitions, so that is M3. So the transitions which are possible or which are allowed for this reaction is E2 and M3. Sorry, here it is M3. So E2 and M3. So correct option for this question is E2 and M3, and this is the CSIR-NET 2016 problem. So there is one more example. Find allowed multiple transition for 3 by 2 minus to 1 by 2 plus. So 3 by 2 minus to 1 by 2 plus, you can see the maximum values of J, they are possible. 3 by 2 minus 1 by 2 to 3 by 2 plus 1 by 2. So J is 1 and it is 2. So J value which are possible for this transition is 1 and 2. And since here is a change in parity, so when parity changes, so electrical odd transitions and magnetic even transitions. So this is the key point. So when J is 1 and 2, so these four transitions are possible. Either it is E1, E2, or it is M2, M1 and M2. Now which are allowed? So when there is a change in parity, E1 transition, and when there is a change in parity, M2 transitions. So the allowed transition for this reaction is E1, that is the electric dipole transition, and M2, that is the magnetic quadrupole transition. So this is the correct answer for this question. So similarly, for this question you can see, so when the transition is from D state, D 5 by 2 to P 3 by 2. So D 5 by 2, so D orbital value of L is, you can see L is 2. So when L is 2, so there is 5 by 2 plus parity is even, and it is in the p orbital. For p orbital, L is 1 and there is a odd parity. So this is the transition which exists for this d5 by 2 to p3 by 2 transition. And now you can calculate the J values. J value will lie between this JF minus JI, that is 5 by 2 minus 3 by 2 to 5 by 2 plus 3 by 2. So J values which are possible, that is 1, 2, 3 and 4. And you can see that there is a change in parity. So when there is a change in parity, so only those transitions are possible, that is electrical odd transitions E1 and E3, and magnetic even transition M2 and M4. So this is how you can calculate the transitions which will occur for this reaction is E1, M2, E3 and M4. But the majority of the transition which will come is the electrical dipole transition. So this is, they have calculated, they have written this answer E1, M2, E3 and M4. So these are some of the examples. So sometimes they have given you the question by giving it in the figure. So you can see that the 4 plus transition, it is being decayed into 0 plus transition, and you have to find which transition will be possible for 4 plus to 0 plus, and they have found that. So for this transition which is possible between 4 plus to 2 plus, you can calculate for each case. So for the transition which is possible from 4 plus state to 2 plus state, so you can calculate the J value which will lie between 2 to 6, because the minimum value is 4 minus 2 to 4 plus 2. So J value which is having 2, 3, 4, 5 and 6. Now there is no change in parity. So when there is no change in parity, then you have to consider odd magnetic transitions. So odd magnetic which are possible M3, M5 and even electrical transition. Even electrical are E2, E4 and E6. So the lower number transition which is having the most probability. So the main transition will be E2 transition for plus 4 to 2 plus transition. So similarly you can calculate for all the other cases. So these are the transitions which I have given, and this is your the 3 and try to find each case which is the major order transitions for each action. So next important basically the internal conversion. And nucleus, it tries to the ground state and so when this nucleus it energy, it loses gamma radiations, because gamma radiation, it is a nuclear phenomena. When this gamma radiation, they are coming out from the nucleus, and there are chances that they interact with this orbital electrons. So there are chances that interact with this k orbital electron, there are chances they interact with l orbital electron, there are chances they can interact with this m orbital electron. And when this gamma photons or gamma radiations, they interact with this electron, and if the energy of this gamma radiation, it is greater than the binding energy of this orbital electron, they kick this orbital electron out of these atoms. And along with that gamma radiation, the electron which is also coming out, and this process is known as internal conversion process. So you can see that this is our excited nucleus, and during the emission of this gamma radiation, it loses its energy to this orbital electron, and gamma radiation, it is being absorbed, and only the electron which is coming out, and this electron which is coming out is known as the internal conversion electron. And this is opposite to photoelectric effect. Now in the photoelectric effect, what you see is, so these are our orbital electrons, and when we are shooting gamma radiation from outside, so when we are shooting photons or gamma radiation, they are kicking this orbital electron, and this process is known as photoelectric effect. Now in this internal conversion process, the gamma radiation which is coming within the nucleus due to the excited or perturbation within the nucleus, and this gamma radiation, it is being absorbed by this orbital electron, and these electrons, they are kicked from this metal surface, and this process is known as internal conversion process. And you can see that, so the energy of this coming electron we can calculate based on the energy of this initial and final state minus the binding energy. So this is h nu, that is the energy of this photoelectron which is coming out, minus the binding energy. And how much energy, if this internal conversion process is only possible if the photon which is coming out from this nucleus which is having greater energy than this binding energy, and based on that we can calculate the kinetic energy of this emitted electron if it is coming from this k orbital, and so and so, and the probability of the k orbital electron, it is maximum, so and so, and on the basis of that we can find out or compare this reaction based on this internal conversion coefficient. Internal conversion coefficient, which is equivalent to number of electrons which are coming out, or number of gamma radiations which are coming out. And this internal conversion process, so the value it changes. So if there is only electron which is coming out, and only in that case n alpha whose value is 0, and n electron which is having the maximum value, and so we can find out the magnetic multipole or the electric multipole transitions based on this internal conversion process. So but I will not go in detail, so you have to idea about this process and how we can calculate this internal conversion coefficient. So this is important for your case. So dear students, so this is the end of my talk, and in this talk I have tried to cover all those important reactions which are generally in the competition examination related with this beta transition and this gamma transitions. I hope you have understand this lecture, and if you have any doubt you can ask any query. So the session is open for doubts. Yes, students.
No, sir. I have no doubts.
Because this is very important topic. So the beta and the gamma transitions, so many of the students, they get confused in the numerical problems related to these type of topics. So try to solve some of the previous year competition problems. I will also take one special lectures in which we will only discuss the numerical problems. We will not go through the concept, but we will only do the important numerical problems from the last 3 to 4 year exams. So then you will get more ideas. So this is, but you have to do a lot of practice to get familiar with this type of numericals. So, okay, students, if you have no doubt, then I close my lecture. See you in the next lecture related with the particle acceleration. So how we can use the various accelerator and how we can accelerate the particles like the cyclotrons, the betatron, the synchrotron, and what are their major roles, how we can accelerate. And alert from Microsoft PowerPoint. Want to keep your ink annotation? So, okay, students.
Okay, sir.
Okay,
Thank you,
dear
sir.
students. Okay, bye bye.